Thank you all. Thanks for coming. I can't tell you how excited I am that it's going to be on the SMPTE YouTube channel later for you all to see. Something for my kids to tease me about years to come. Video compression, the basics and beyond. Nothing happened. Here we go. I don't do a lot of PowerPoint normally. I'm coding, so you'll have to bear with me. Did you see the fancy animations there? This is all of the it's not all of, this is a selection of various codecs that we might use in our day-to-day work here at Telestream. I'm not going to be able to cover all of the details of each one of them. What I want to really do is sort of walk you through the major ones through time, giving you the basics of some simpler codecs from some time ago, and then walking you through some of the more advanced techniques that we're using in modern codecs today and tomorrow. All right, so this is me. Most exciting thing is obviously my dog here. I think Scott covered most of this, but one thing that I do is I do a tech talk every Friday to the engineers here at Telestream. It's in this room here, and I pick a topic at random and I talk a little bit about it, try and bring people up to date on what's going on. So I should be way better at this than I actually am, so please bear with me. All right, so a timeline. This is not all of the codecs that were even on the first slide, but it hopefully gives you an idea and maybe some of the names that you'll recognize here. So we're going to start all the way back here in 1989 with the JPEG codec. So you might be familiar with JPEG as an image compression format. A lot of the pictures that are on the internet coming into your browser are compressed using that JPEG standard. But it's also, I think of it as a video compression standard. If you just compress one picture followed by the next with JPEG and then play them back in succession, you get a video codec. So we'll talk about how that works. And then we'll talk about how that technology was extended by the motion picture expert group into MPEG-1 and then MPEG-2. Then probably the codec that I see most, even today, is H.264 or AVC. Those names are synonymous. Standard all the way back there in 2003, which is amazing when you think about how that's still so prevalent today. And then I'm going to skip forward to HEVC, which is still gaining adoption, and then VVC, which is a standard that's still in development. So we'll talk a little bit about what are the tools that are available in that. I got a lot of material to cover, but I am happy to stop and clarify any points as we go along. Just raise your hand. All right, video compression. So let's just define our terms before we start. I'm just going to define that as trying to represent an image or a series of images in less bits than it would take if I didn't do anything, if I just tried to send raw pixels that came out of a camera sensor, let's say. But if I'm trying to use less bits, there's a price to pay. And the price to pay is in quality. The less bits I use to transmit that video, the worse image, subjectively, I'm going to have my users experience. So I did a bit of fancy work here. You can see it's compressed on the right-hand side. It's not compressed on the left-hand side. And we've got some artifacts. Call them compression artifacts, if you like. OK, there's another way to do this. I can start off with not much compression, and I can get more and more compression here. Okay. Better, worse, better, worse. I should have been an optician. OK, so how can we go about using less bits than just sending the pixel data that comes off of the camera sensor? I'm going to talk about a concept of a transform. It's a way of representing something in some other format that allows us to look at the data in a different way. And then by looking at that data in a different way, we can immediately see a tool that we might use to not use as many bits before. I wanted to think of an analogy for a transform, and I couldn't come up with a good one. I thought of maybe slide rules, but I don't know how many people are actually familiar with slide rules anymore. But the idea with a slide rule is that you could transform a number to a logarithmic scale, do some addition, transform the result back from the logarithmic scale to the linear scale, and you've done a multiplication, relying on the fact that log xy is equal to log x plus log y. Okay, that may not help. There's a transform that allows you to look at a number in a different way and then makes the math or whatever you're trying to do easier. Here's another example and much more relevant for what we're doing here. So color, we typically think of video as being represented by an R, a G, and a B, a red, green, and a blue component. And that's because of, I guess, three things. One is that's the way your eye works. You know, you have receptors in your eye that are sensitive to red, green, and blue light, and by combining the signals coming into those receptors, you see color. It's also how, in a camera, if you had a CCD, you know, those individual receptors in the camera would be receptive to those wavelengths of light. And then also in a TV, you know, you have red, green, and blue lights or pixels that combine together to form color. So I don't think that should be a surprise to anybody here. But we can think about that in a different way. Actually, before we do that, let me do some quick math. I'm going to try and limit the amount of math. I originally had this presentation, and I had all kinds of equations all over the place, and I ran it by my kids, and it was just not going to work. So there's very little math now in the presentation. But here's a little bit that shouldn't be a problem to anybody. This picture is HD size, high definition video, which is 1920 pixels by 1080 pixels. We got three components, the red, the green, and the blue, 50 frames a second, 8 bits in a byte. That's 2 gigabits per second. So even my fast internet connection at home, we're not going to be sending that down over the internet to my screen. It's just not going to work. We have to do something. Okay. So here's the transform I talked about. We can take the red, the green, and the blue components, and we can transform it into 3 different representations. The bottom left looks like a grayscale or a black and white picture, and that's what we call the luminance image. It just represents the light or darkness of all of the pixels in the image. And then the other 2 chrominance planes here, they represent the color information in the picture. So we've done this amazing transform, and we still have got 2 gigabits per second. We haven't done any compression yet at all. But we're now able to look at what we had originally coming off of the camera sensor in a different light. Okay, you may have seen this on the internet, maybe not. It's one of those optical illusion things. It looks like what you're seeing here is a color image, sort of. But what it actually is a black and white picture with some diagonal lines of various colors on it. It's supposed to represent the fact that your eye sees black and white luminance levels at a greater granularity than it sees chrominance color information. So you can get away with transmitting less color information and still get a good subjective experience. Okay, so what if we took our images and instead of sending the full HD version of the color images, we just sent a smaller representation, maybe half the size here. And in fact, that is what we do. We're able to get away with sending only half the data, 1.2 gigabits per second here, because the color information, when it's restored to its full size on your screen and combined with the luminance, doesn't have to be sent at such a fine resolution as the luminance does. Is that making sense to everyone? We have lots of names for the different ways that we can do this and the different resolutions of the color that we send. But pretty much most of the video codecs that I work with start off by making this transform and reducing the amount of color information that we're going to send. Okay. So here's something that somebody who had too much time on their hand did. They took Excel, and what they did is they went into every cell in their Excel spreadsheet, and they put a number that represented the light or darkness of that pixel. And then they used Excel. You can put a little formula to turn that number into how the background of that cell is rendered in terms of from white to black. And you can build up a picture if you have the desire to do so. I'm going to use something like this to try and explain the next step here. This is perhaps the hardest thing to explain, and the thing that I was going to use math to explain to my children. And I'm going to try and do it in a way that I made up. So we'll see how it goes. All right. So if we zoomed in really far in this picture, then I could imagine that I can represent this just like the cells in that spreadsheet in my previous example. Each cell's got a number. In my case, it's a number from -1 meaning black to 1 meaning white. And I've put some random numbers here that are supposed to be representative of a little patch of this image. Okay, so this thing I made up, I'm going to call it pattern math. You won't find it in any textbooks. Pattern math. So I've got, this thing's got a fancy pointer on it. Let's see if it works. Okay, so I'm here on these 2 pixels here, the 0.11 and the 0.311. And I want to transform them, just like I did with the color, into a different representation. So instead of sending down the 0.11 and the 0.311, I want to send down some different information. And my contention is that for any combination of numbers, 2 numbers, I can send down some combination of the pattern white-white and some combination of the pattern white-black. So simple example. Let's say that those 2 numbers were a half and a half. I could have an alpha of a half, so I get my 2 white values multiplied by a half, and 0 of my white-black pattern, and that would give me 2 0.5s together. I'll give you the example that I've got here. So I'm trying to get 0.11 and 0.31. So if I take 0.21 times the white-white pattern and minus 0.1 times the white-black pattern, it'll give me 0.11 and 0.31. So I'm taking patterns and adding them together to form the 2 pixels that I got there. I haven't saved anything. Before I did the transform, I would have had to send the values 0.11 and 0.31 down the wire. Now I'm sending down the values 0.21 and minus 0.1 down the wire. I'm still sending down 2 numbers. But I'm going to use this information in a minute to to help me send less bits down the wire. I got some nodding and some like totally baffled looks. So maybe I'm building on this, so hopefully it'll become clearer.
Why are you only considering the cases of white boxes together and white and black? Is there no black?
How did I pick these 2 patterns to add together? Yeah, I will come to that, because you can't just pick any 2 patterns and add them together. They have to be what would be called orthogonal if you were a mathematician. They have to be things that don't have any I don't know. I can't explain it without using the word orthogonal.
Overlap.
Yeah, there's no correlation between the 2. Like if I had another white pattern, then there's a high correlation between the 2 patterns, and adding them and it wouldn't allow me to make a pattern something that wasn't just 2 squares with the same number in. This might help, or it may confuse you more. So I can do the same thing with 3 numbers. So instead of just taking the first 2 numbers, which we did the first time, I'm now going to take the first 3 numbers. Now my patterns have to change in order for me to be able to add 3 patterns together to make any particular combination of numbers. But if I pick an all-white pattern, a pattern that goes from sort of a light to a dark, and a pattern that goes light, dark, light, then I can pick, for any number that you choose to dream up, I can pick a value of alpha, beta, and gamma that when I add those together will give me this result here. So in this particular case, to get minus 0.11, 0.311, and minus 0.57, I use these numbers here. Okay, so how did I come up with the patterns? This technique is called a discrete cosine transform, and the reason it's called that is that we use cosines to generate those patterns. So the red line there is the graph of y equals cos of 0x. Because cos of 0, cosine of 0 is 1, it's just a line of y equals 1 here. Then the next line, the blue line, well, let's do the purple line. Y equals cosine of x. You get this like half wave here. Y equals cosine of 2x. You get the full wave here. And if I pick 3 equidistant points, I end up with those values that I was just using for. So that's the answer to the question. How do I pick the patterns? I use cosines to derive what those values are going to be, and the math works out that those end up being orthogonal. Okay, now it gets good. What if I had 8, not 3, but 8 of these pixels that I wanted to do? Okay, my patterns get more complicated, but just using those cosines, I can generate what those patterns need to be, and I can come up with my completely randomly selected numbers. I can find a value of alpha, beta, gamma, and whatever those other Greek letters are that come up with the answer here. Okay, with me so far. I haven't achieved anything, but I've been able to take any number of numbers and transform it to a different set of numbers that represent the same thing. It's just that before the numbers represented pixel values, now they represent the addition of patterns. Okay, why did we do all that? Well, it turns out, let me go back one, that from a subjective point of view, your eye is just like it can see luma differences better than it can see color or chroma differences. Some patterns are easier for the eye to differentiate than other patterns. And so it turns out that we would like to apply more weight or more resolution to the patterns at the beginning than we would at the ones at the end. So I could say, for example, just not send the last pattern down, and I would still get a pretty good representation of the numbers that I originally started with, at least from a visual point of view. And that's where this idea of quantization comes from. If I wanted to send these numbers, these are my coefficients for alpha, beta, gamma, etc., I could decide how many bits that I wanted to use to actually send that number. And the more bits I use, the more precision I have, and the better that particular pattern is represented in the bit stream. So if I want to use 8 bits, I use these numbers, 6 bits, 4 bits, 2 bits, these numbers. And we really do that. We take the patterns that are all very solid, and we use a lot of bits to use that information, but we quantize or use less bits to represent the numbers that represent the patterns that have got a lot more changes in them. But we don't just do it in 2D. It's an image. We do it in 3D. And the patterns aren't as simple as I showed. These are actually the patterns that I have here. So for any 8x8 image that you can dream up, you can apply some combination of these patterns and reconstruct it. And we just happen to quantize the patterns down this end, or nearest to this block, a lot more than we do the patterns down at the far end. Okay, let's take a look at an example. This is a contrived example. It's very symmetrical, this picture that I'm trying to compress here. So this is an 8x8 block here. Ignore the red and the blue, that doesn't mean anything. It's just an image that's got 2 different values in it. And when we do the pattern math, or we do actual real math, then you end up with coefficients that look like this. So it only actually really takes 4 values to send the information to transmit this picture, rather than the 64 it would have done if we hadn't applied that transform. The idea is, by the process of taking advantage of symmetry in this example and the process of quantization, we want to try and get as many of these coefficients to be 0 as possible, because it doesn't cost us any bits to send a 0 coefficient. This is just a tiny detail, not worth paying a lot of attention to, but I want it to be complete. When we get those coefficients, we actually will scan them in what they call a zigzag order. So this set of numbers down the bottom here is just me running through this matrix of numbers and writing them down, 509, 0, 0, 0. as though I'm traversing them in this exact pattern. And we end up with this code here, or this series of codes that we want to actually transmit. And that's where the next thing comes in, which is entropy encoding. So I've thought about different ways of explaining entropy encoding, and this is the best way that I've come up with. Does anyone know what this machine is here? It's called a linotype machine. It's for what you'd have on a printing press. A linotype, I think, is where the name comes from. The keys are arranged in a funny way. You know, we're used to the QWERTY layout on our keyboards. They pronounce this type of keyboard going down here an Etaoin-Shudlu keyboard. Really, they do. The reason they do that is that this is the order of prevalence of letters in the English alphabet. So E, most common letter, T, next most common letter, and so on and so forth. Okay, so how can we take advantage of that? Okay, if I wanted to compress the string Brian is cool, and why wouldn't I? There's a number of ways that I could do that. I could represent, I don't know if that helps. I can represent each of the letters by a Unicode value. So in this case, there's a table somewhere, and if I looked up the letter B, it would have the code 0042. There's 11 letters there, 16 bits in each of those codes, 176 bits. I could transmit Brian is cool. I could choose to do it with a reduced set of characters, maybe just the ASCII character set, so that would be 11 times 8, which would be 88 bits. I could even just choose to use 26 letters of the alphabet if I wasn't that worried about capital letters or not, 55 bits. But I can do better if I take into account the distribution of letters in the alphabet. What I mean to say by that is, if I use less bits to transmit a letter E than I do to transmit a letter Z, or Z as we would say back home, then I can save in the overall bit rate. So I'm playing off, I'll spend a little bit more to transmit a Z than I would do normally, and I'll spend less to transmit an E than I would do normally. And on average, it turns out that I spend less bits overall if I know the distribution. So this is a very simple example. I've listed out all of the letters here and their frequencies, and then I've turned the table around. So now I've got the letters ordered by their frequency with E at the top and Z at the bottom. So the frequency here, after the frequency, this may be a little small for you to see, I've put a code. So I'm going to represent E as 000, I'm going to represent T as 001, etc. And I'm going to represent Z as this great big number 111111001 here. So a lot more bits to transmit a Z than an E, and if I write it all out, I can get it down to 50 bits here. Now there's lots of ways that you can derive this table. How do you take a distribution of symbols and assign a code to each one of those? This is the most simple way that I know how to do it, which is that the number of ones at the beginning of the string represent how many bits I'm going to use to transmit the rest of the number. So in this case, if I'm decoding a number, let's say this one here, 111, in a bit stream, the 3 ones at the beginning tell me that I'm going to have 6 total numbers or 3 following numbers in the code. And so I pull out 001. That's my full code. I can look it up and see what letter that is. I'm going to recap just real quick there. So the idea here, what I'm explaining is that if I know the distribution of codes that I want to transmit, and some of those codes are more prevalent than others, then I can choose to use less bits to transmit the common codes than I can to transmit the uncommon ones, and overall save on bit rate. So now how does that apply? When we were back here, we had some codes that we wanted to transmit. What I need to do is just convert those into a series of bits. And the way that that's done in JPEG is with a Huffman table. Before I go on to that, though, why Brian is cool. Well, obviously Brian is cool, but the reason that I put that there is when I was in England learning to program, this is what I learned on. I was like 12 years old, these things called a ZX Spectrum. You probably called them ZX Spectrums over here. We'd go into Tandy's, which was our equivalent of Radio Shack, and we'd write this little program here. Print Brian is cool. That second statement there, that was the real trick behind this. This put it into a mode where would no longer respond to any of the keystrokes on the keyboard, and then go to 10. And then for the rest of the day in Tandy, everybody would be quite aware how cool I was. All right, sorry, it's minor distraction. So this is another way of generating those codes. It's I don't know what they call it. It's a Huffman tree, I guess. It generates a Huffman table. This is just I'm not going to explain it because mostly I can't remember. But it allows you from any arbitrary set of symbols to generate codes for them. So I put all of the letters that are in Brian is cool here, and by traversing the tree, I can get out the codes. You shouldn't worry about it too much. There's a lot of different standards that use different ways of taking symbols and making codes out of them to put in the bit stream. Yeah.
So if you don't have a fixed bit length, how do you decode? It's like a 111000 could be one letter, or it could be two letters.
Yeah. The magic of this way of doing it is that doesn't happen with this. If you just read out the bit stream until you matched one of those codes, you would only match one of them, and then you can move to the next code. It's much easier to explain, though, with the one that I did earlier, where the number of leading ones represents the number of bits that you have to now read from the bit stream. So if I see, well, I explained that before. To answer your question?
Saying the last three bits are like the terminator of the string, and there's only 4 of them on your previous slide.
Yeah, this is not. This is a number of bits that. So if you see this here, I feel like I've done this wrong. I said it wrong, I think. You keep reading here until you don't have a 1 anymore, and then you read 3 bits off the end. So it starts off with these codes that are, you get 4 codes that don't start with a 1, and you get 4 codes that start with a 1, then you get 4 codes that start with 2 1s, and you get 4 codes that start with 3 1s, etc. And so if you're reading from the bit stream, and I read 1 1 1 1, so I'm down here on the 4th one, and then I get something that's not a 1, I know I have to read 3 more. I can then look up this code, and then I just can start reading again until I run out of 1s. So this is a much easier one to sort of explain. The Huffman table thing generates it automatically, but you have to trust that it's generating codes that can't be ambiguous in the bit stream. All right, so this is everything I talked about, and it is all of JPEG compression. So this is I'm slightly stretching the truth because there are some extensions to JPEG that make it more complicated, but most of the JPEGs that you get on the that I see on a day-to-day basis just follow this very simple method. We're going to take the picture, we're going to split it into luma and chroma planes. We're only going to treat the chroma planes with less precision than the luma, DCT, pattern math stuff, sorry. Quantization to remove some of the bits in the higher patterns that we don't see as clearly, zigzag the coefficients, and turn those symbols into a bit stream using Huffman encoding.
I think I understand where you can maybe say bits are more along the way, except for the zigzag. How does that save you?
Oh, it's worth, yeah, I did gloss over that. And it is fairly easy to explain. what we're trying to achieve here is getting the most zeros in a row. And it turns out that it's very unlikely, it's very likely to say that this one over on the right-hand side is a 0, because it's one of those high-frequency things that we're going to quantize quite a lot. But it's quite likely that this one is not going to be a 0, because it's a very low-frequency thing that we're not quantizing very much. So if I just ran the ordering from here across, I would probably go here, and this would be a 0, but then I'd jump back over here, and then this would be not a 0 again. But if I do it in a zigzag order, we're sort of clustering together things that are likely or not likely to be 0. So at the beginning, as we're zigzagging through it, we're probably going to have a lot of numbers because they're not being quantized. But as we get further and further through the zigzag, now we're into these high coefficients that are more likely to be 0. So we cluster the zeros together. To answer the question. Okay. So how did we do so far? What time did I start? Half an hour ago? We were up to 1989.
Back to the zigzagging, would you still send the zeros across the wire?
Yeah, the way that that's normally done is the symbol says I've got 5 zeros and then a number, or I've got 11 zeros and then a number. So you're sort of you are saying how many zeros that you've got, but it's
also termination if the rest of it's 0.
Sure. Yeah. Okay, so 1993. MPEG 1. Here we go. So I talked about JPEG being, been thought of as a bunch of compressed images just played back one after another. But it turns out that if you're playing stuff back at a sufficient frame rate, the next frame, it looks very similar to the frame that you've just sent. Maybe a great swath of it is the same and just some detail is moving. So I've tried to show that here. I've taken 2 frames in succession of my crowd running clip. And you can see that when I do a difference between the two, all of this area at the top here where the clouds were, that's not really moving at all. So there's not really any difference at all. So sending those pixels again is just a waste. If I could just say, just use whatever we had in the last picture for those cloud pixels, that would help me a lot in saving some bits. And that's exactly what we do. So how do we do that? There's this concept called a motion vector. So I'm trying to explain this by a very simple picture that has a ball that's moving in it. And each successive picture just shows the ball in another position. So if I just did a difference image between the first one and the second one here, I get that black and white image there. And the problem with that is that now the difference image actually contains more information in it than either of the 2 ones that I started with. So I can't just do a difference between the previous one and the next one, because I might end up with, as something moves, I end up with a difference that has that moving thing twice in the result. So what I have to do is I have to break the image up into pieces, and I have to say for each piece, where in the previous image do I think that there is something that looks like the thing that I want to put in this image? So hopefully that makes sense from this drawing here. In this second one, I've drawn a little motion vector on here. What this means is that when I'm trying to encode this picture here, rather than encoding the ball at this position here, I simply say, for this block here, I'd like you to look in the previous picture in the direction of where the arrow is pointing. So that the arrow would have a strength to it. It would point almost exactly at where the ball is in the previous picture. And for this block, and by block I mean a sub-picture of this picture, we can use the information from the previous one. And that gets extended over the whole picture, so you probably can't see that. But on here, all those little red and blue arrows are motion vectors. So pointing to where in the previous picture I could pull that data from and not have to then send the same information again. Or maybe I use the previous picture to predict what that block's going to look like, and then I make some fine adjustments to it. But I don't have to send as many bits for those fine adjustments as I would do if I sent the whole of the block. Everyone okay with motion vectors? So that manifests itself, we see this on a daily basis when we're in the work that we're doing in the frames being categorized into one of three, in this case, possible types. So an iframe is what starts off our sequence. An iframe is just like a JPEG image. It's completely is self-contained, and we pass all of the information for that picture. But then we have a p-frame, and a p-frame is a predicted frame. We use motion vectors that point to places in the iframe to help us not send so much data for the p-frame when we're constructing it. And then we have these b-frames, which are bidirectional predicted frames. And what they do is they are allowed to use motion vectors that point either previous in time to the iframe or forward in time to the p-frame. And it may be that it chooses one or the other because there's a good prediction in one of those two directions. Or it may be both, that we don't have a good match in either the iframe or the p-frame. But by combining something from one and something from the other together, we can form something that we can use as a prediction for our blocks. And that just repeats with the p-frames referring to its previous p-frames until we get to a point in time where we inject another iframe. And we do that periodically because if there's some corruption in the stream, that gets propagated forward as each of the subsequent blocks refer back to that corruption. And so it's nice every once in a while to just put a nice firm stake in the ground and say, okay, this is a fresh picture, and we'll start our stream again from there. Okay, so that was MPEG 1. MPEG 2, 1995, didn't, as far as I can tell, add a lot of new tools to our compression tool set. The standard defined bigger pictures and different chroma samplings, how much we do resolutions on those chromas. But I can't think of anything that I want to add to the tools that I've described so far for MPEG 2 over MPEG 1. So then we're going to jump all the way forward to 2003, H.264. And I think I have slides for each one of these. So I'm just going to jump to the slides. So the first one is...
I have a question for you.
Sure.
What determines the frequency of inserting a new iframe?
I don't know for MPEG 1. Don't see it a lot. In MPEG 2, it's up to the person configuring the encoder. So there's some standards. So, for example, XDCAM is a Sony standard, and they very prescriptively say, this is the pattern of I and P and B frames, and every 15 you're going to have a new I, or whatever the standard says. But MPEG 2, the specification, the general specification, would let you do whatever you wanted in terms of that. Generally speaking, you get better compression efficiency by having longer streams, longer runs before an iframe, but you just run into the problem that you then have to wait longer if you've got a corruption before the picture gets refreshed again. Okay, H.264. So in MPEG 2 and MPEG 1, we had blocks that were 16 by 16. I'm going to use the word blocks just very generically in this presentation. Different standards use different words. There's a now I forget the codec units, CUs and CTUs or whatever in the new specifications. But I'm just going to use the word block to refer to some square piece of the screen that we're trying to encode. So in MPEG 2, there were these 16 by 16 blocks. And in ABC, we're allowed now to split those up into smaller blocks, like this one here, say, for example, because we may be able to find a motion vector for this little square here that's slightly different from the motion vector that we would want to use for this little square here, and we get slightly better efficiency by doing that. Intra-prediction. Okay, so let's say that these are my blocks that I'm trying to reconstruct in my picture. So you know, the top left-hand side block, I get this one. The next one I reconstruct like this, and then the next block I get here. So what do I think, if I didn't know anything at all, can I make a prediction for what this block is going to look like? Well, I think I can. You know, I could maybe use the block above it and just predict it's going to look like that, and you know, that may give me some information that I don't have to transmit that I would have had to do if I didn't use that as a prediction. Or maybe I can use the block on the left and it looks like this. Or maybe I can combine the two and it looks like this. I think this is probably a pretty good prediction for what that might look like. And if I use that prediction, maybe I don't have to send so many bits to represent that block. I can just send the difference between what I think it might look like and what it actually looks like. Okay, this is tricky. This is a really big one. So let me go back to the slide. Oh, I didn't realize it was going to do that. You will, if you get in the compression world, you'll see this referenced a lot. CABAC, they pronounce it. Context-based adaptive binary after arithmetic coding. I think it's quite a complicated concept, so I'm going to explain it in the easiest way that I can. Oops. Darn it. No. Okay, we're there. It does require you to know binary in order for me to explain this, so I'm going to presume that you do. Most people know in binary that, well, in starting with our decimal number system, right? The first digit represent ones, and then tens, and then 100s, and then 1000s. We multiply by 10, or it's 10 to the power n as we go up here. In binary, this is a 1, this is a 2, this is a 4, this is an 8, etc. What people don't always know is that you can go the other way. You can put a decimal point, and so the first digit behind the decimal point is a half, and then the next one is a quarter, and the next one is an eighth, and the next one is a 64th. Okay, so let's say that I have this string here, BAACCB, and I wanted to represent that in some binary bit string. I could just assign a 2-digit binary code for each of those letters. So let's say that I call B01, A00, and C10, or the equivalent of 0, 1, and 2 for A, B, and C. Then I would produce this string here. But what you'll see in that is that we're wasting a bit, because our code of 2 binary bits could really represent 4 different symbols. I could represent A, B, C, and D, but there aren't any Ds, and so I'm wasting the 1, 1 code because it's not there at all. And so a different way of doing that would be if I used not binary, but trinary. I don't know if that's the right word for it, a base 3 system. And I'm doing the fraction thing that I talked about, like a half, a quarter, an eighth in binary, but that's a third, a ninth, a 27th in trinary, ternary, I don't know. I'm going to represent this same number in that it's going to be 0.1 for a B, 0, 0 for the 2 A's, 2, 2 for the 2 C's, and 1 for the B. And if I was to convert that to a fraction, then it would be just adding up this here. So I can convert a string of numbers into a fraction that ends up being a number between 0 and 1. Now, I could represent that same fraction between 0 and 1 as a binary number. This binary number here actually equates to the same number, give or take. And I can transmit that down the wire as 1, 2, 3, 4, 5, 6, 7 instead of the 12 that I would have originally. A lot of confused looks. I figured as much. I don't have a better explanation than that. There is another explanation. I won't go into it, but it actually involves turning the codes that we have into a fractional number between 0 and 1, and then transmitting that number as a binary sequence. And that's where the binary arithmetic coding nomenclature comes in. All right, I'm going to just apologize and move on. Deblocking filters. Okay, so I've drawn here the blocks in my image that I'm trying to reconstruct. And you saw this in that original picture where we had, where I was showing you the compression artifacts, where it looked all blocky when I had the compression. The reason that is that we might have a different set of quantization for this block as this block. And so on the border between the two blocks, you see what we call blocking, or there's compression artifacts. So I've attempted to do this over here. I've blown this up bigger. Oh, come on now. It looked really good in the... Darn it. I don't know how I can make that better. Okay, I'm going to describe how it looks on my computer screen, not how it looks here. Along this line here, this half is much darker than this half here. So you end up with a block because over something that should be a monochrome color, it's actually much darker on one side than it is on another because it's in a different block that we've reconstructed. And what the deblocking filter does is it attempts to smooth over that harsh transition. So it's just a conventional filter that you would, like a low-pass filter or something like that, that would go across the transition and would blend the one into the other and kind of hide those boundaries from you. So that's done on the decoder side, but the encoder knows about it so that it can factor that into the next pictures that it transmits. That's very disappointing. One more thing just to say before we move off H.264. The way these specifications are defined is from the point of view of the decoder. So the specification that MPEG or whoever's making these specification produces tends to say, you know, this is what the bit stream should look like. If you see this, the decoder should do this. It doesn't make a lot of reference to how an encoder should work. And what that does is it leaves the encoder vendors a lot of ability to innovate in the way that they're creating these bit streams. And I just want to give you an example of something that I think is particularly clever that one of the manufacturers did in order to create these bit streams more efficiently. So what I have here is, this is the same, it's a sequence of images through time. And there's two balls that are running through these images. The red ball starts in the iframe and immediately leaves. Whereas the green ball, it stays in that picture for a good long time here. And what this particular encoder vendor did was, they said, well, what I could do is I could track using my motion vectors how many times a particular pixel in the iframe is used in all of the subsequent frames. So I know that a pixel that's somewhere in the midst of that green ball is used 1, 2, 3, 4, 5, 6, 7, 8, 9 times in the subsequent frames. But a pixel that's in the midst of that red ball there is only used 1 time afterwards. And so what I'm going to do when I'm trying to work out my quantization values or how many bits I want to invest is I'm going to invest a lot more in these pixels in the green ball than I am in the pixels in the red ball. So I'm going to represent that green ball a lot more accurately than the red ball because I get to reuse that investment all the way down the line here. Whereas any investment I put in the red ball, that's gone. It's fleeting. Probably nobody would even notice.
Right?
Yeah.
Does that require a multi-pass structure configuration of going through the...
Yeah, so this particular encoder vendor is the X264 uses this technique. I'm sure other people do as well now. And they have what they call a look ahead. So you can configure, I want to look ahead, let's say, 40 frames. And so what that means is you've got to put 40 frames into the encoder so it can do this analysis before the very first picture comes out of the encoder. Did somebody say something?
You want a lot of latency.
Yeah, a lot of latency by doing that.
Oh, wow.
That's right. That's right.
There are a lot of trade-offs with that.
Yeah, and memory as well. You know, storing 40 uncompressed pictures in memory, not a big deal for us in the software game, but you know, maybe you've got some hardware limitations that you have to deal with. All right. You still with me? You want me to carry on? Okay. We're getting there. HEVC. This is. I still think of this as being cutting edge, but it's been out there. When 2013? Did I say? I can't remember. It's a while. So just some of the things that are inside of this. We've got a larger block size. So before we had 16 by 16. Now we've got 64 by 64. I'll talk about why that's important. The more intra-prediction modes, like how, you know, I showed you 2 intra-prediction modes in that slide where we either took it from the top or the bottom or the combination, sorry, the top or the side of the combination. But now there's 35 different ways that we can try and predict what that block's going to look like. Advanced motion vector prediction. This is, you know, instead of sending the motion vector information for each of those blocks, maybe we can predict what the motion vector is based on something other motion vector that's also in the picture. It's all very clever at this point. We added another type of filter. So I explained the deblocking filter, but now there's these other filters as well to take account of other artifacts like ringing in the picture. And then there's apparently an enhanced CABAC, which is probably even more difficult to explain than the first CABAC. All right, I just want to explain why block size is important. We've gone 64 by 64. It's a trade-off. It's another one of those trade-offs. So if I was to divide the picture up into just 2 or 4 blocks, then I would only have to send 4 motion vectors, and there wouldn't be a lot of overhead in sending those motion vectors. But the granularity of those big blocks wouldn't be very accurate and wouldn't be helpful in what I'm trying to do. Let me explain here. So in this big block example, I've got a blue circle and a red triangle, and when I go to the next block over, the red triangles move to the right, the blue circles move down. If I'm trying to predict, say, this block that the red triangle's in, and I look to my previous frame, there is no red triangle on its own in this previous picture. So there's no block that I can refer to that really accurately predicts just the red triangle on its own. So big blocks, too big a blocks where it's not good because objects might be moving independently within the block, and therefore those blocks aren't good predictors of objects moving around. Too many blocks is also a problem. So let's say I went crazy and I sent a motion vector for every single pixel in the image. Now that's great. I can really easily predict what every pixel is going to be, but I've got to send 1920 by 1080 motion vectors in the bit stream, which has completely blown my bit budget. So there's a compromise. And what we've ended up with is the ability to be able to subdivide big blocks into smaller blocks. So if we need a big block, we'll use a big block. If we need a smaller block, we'll send a small block. Okay, I didn't have much on HEVC. What I really wanted to talk about was VV. So I don't know if I've just been throwing acronyms around. HEVC, high efficiency video codec. VVC is the specification they're working on at the moment, due to be released in October of this year. It's the versatile video codec. Larger block size. We've gone from 64 by 64 to 128 by 128. We're not now limiting ourselves to square blocks. We can go rectangular blocks. Many more inter-prediction and intra-prediction modes, and the ability to be able to combine them together. So maybe we use another block within the picture and something from a different picture and combine them together to try and predict what our block's going to look like. The other ones I'm going to explain with slides. So this is semi-interesting. This is dividing the big block into smaller blocks. So the way that works is you can first divide it into quarters if you want to. You don't have to. Then you can take each of those individual quarters and you can divide those into quarters if you want to. You don't have to. And then for each, once you've done quartering as much as you want. Now you've got a choice. You can divide that block in two vertically. You can divide it in two horizontally. You can divide it in three vertically. Divide it in three horizontally. And what you can, what you can end up with is, some big rectangular sections here. So that helps if what you're tracking is something that looks like a big, that fits in a rectangle and moves around rather than something that's square. Overlapped block. I talked a little bit, I wish that other slide had worked better, where you could see that where you had two blocks that were up against each other, there's this line that gives you these artifacts that look like blocks in your final image. So one way that they've been looking at trying to alleviate that problem is by overlapping blocks that you reconstruct. So, in the old method, you'd have two blocks. We'd reconstruct this block, we'd reconstruct this block, and then there might be some discontinuity between the two. But now, cue fancy animation, we might reconstruct them like this and merge them together over the join so that those transitions there aren't quite as abrupt. This is a really good one. I didn't realize they had done this. I think this is going to be huge. In all my explanations so far, when I've wanted to find a motion vector, I'm trying to reconstruct this block here, which is a red square. I'm going to look in the previous picture, see if I can find a red square, and if I can, I'm going to use it and point to it with that motion vector. But what if in my previous picture it looked like this? Now, that red square is just as good as a basis for this red square over here, but I can't use it because it's in the wrong orientation. Well, what they've done is they said, no, that's fine. Rather than just having 2 degrees of freedom for your motion vectors, now we've got 6. We can cope with translations, size changes, rotations, skews. This is interesting. I've wrestled with this one and explaining it because the explanation I'm going to give isn't the exact thing that they do inside of VVC, but it's the best way that I can explain what decoder side motion refinement is, or motion prediction. So same example again, things moving around. I got an in-between picture. So this in-between picture, the triangle's motion vector is coming from 3 from the left. In the next picture, it's 6 from the left here. But I've had to, in order to do this, I've had to use bits to transmit the 3 to the left information and then the 6 to the left information in my bit stream. But the decoder could actually maybe help me here, because if the decoder was able to do its own motion searching, so it was able to search from this picture into this picture, and then say that probably in the in-between picture, that red triangle is halfway in between, then the encoder wouldn't have to send over the motion vector for the middle picture because the decoder would already know it. So what we're doing here is we're putting a little bit of extra burden, or maybe a lot of extra burden on the decoder to go around and do its own motion vector searching so that the encoder doesn't have to actually put that information in the bit stream. So it's not that we can get really any better quality, or maybe we're only getting better quality because we've got extra bits that we can spend on quality. We're just saving the encoder the trouble of sending over motion vectors by letting the decoder do a lot of that work. Almost there. Triangle partitions. So what if we had, the encoder was trying to encode a block like this, and in the next picture there was a green square over here, and in the previous picture there was a red square over here. Well, now we can do that. We can put into our information that, yeah, we're going to use the green block from over here and the red block from over here, but rather than just merging those pixel values together in the standard way, we're going to say, no, this half of the block, or this, whatever section of the block comes from the forward picture, and this other section comes from the previous picture. And then I think this is finally on the tools that we use. I talked about DCTs. I think that this made some sense to you of how we use a cosine to determine the patterns that we're going to add together. Question that should come up, but never does, is how come you're using cosines and not sines to do this? You got
Can we get the imaginary number problem with the sine transforms?
No. You sort of can think about it that way, because a Fourier transform is really, you could consider the addition of a cosine and a sine component, and maybe you imagine one to be imaginary or not. But that's not really the problem. The problem is that the very first pattern that we generated here comes from cosine of 0, and that produced a 1, 1, 1 pattern here. But if we did the same thing with sine, and we did sine of 0, then unfortunately the sine of 0 is 0. So that's the pattern we can't use, because any sum of 0 is 0. It doesn't make any sense. And so you can't represent a flat surface with a discrete sine transform. Or maybe you can, but you've got to use a whole bunch of weird signs added together to make something that looks flat. And because most of what we're trying to encode is flat, that makes no sense at all. And so if what you're trying to encode is not something flat, maybe something that's got a gradient to it, then a discrete sine transform is a perfectly reasonable thing to use. And so what they've done in the VVC standard is said that we can actually switch. This block, maybe we'll use a DCT because it's flat. This block, discrete sine transform, works better, and we'll use that one. And so they switch on a block-by-block basis whether they're going to use one transform or the other. Quick word about versatility. So it's called the versatile video codec. I don't have many points here. The first one is, for versatility, a lot of video that we want to encode these days isn't just coming from a camera. People are trying to live stream their games, there's animation, there's lots of other things. And so a particular codec that traditionally would have been tuned for a natural video scene perhaps doesn't work so well on some of those synthetic video scenes. And so that's built into this codec, the thought that we would be wanting to encode alternative content. Reference picture rescaling. I think this is important. I did this with the motion vectors before, but when we're transmitting stuff over the internet these days, quite often we've got these adaptive bitrate streams where we start off at one bit rate, but then our internet connection becomes better or it becomes worse, and we switch to a different resolution. Well, what happens there is, on the switch to the new resolution here, we can't use a motion vector anymore because the previous picture doesn't look is a different resolution than the one we've got, and so that vector doesn't point to an appropriate place in the picture anymore. So they took care of that. I'm waving my hands here. I don't know how, but now you can do this. You can switch streams, and you can still have motion vectors that point to the picture that was from a different resolution. They're obviously adding this with a view to live streaming and switching resolutions and not having to transmit as many iframes as you would have to if you didn't do this. And then the last one, independent subpictures. So this is an example where maybe it's a set of VR goggles, and you've got a preferred viewing direction, but then you've got the 360 for when you look around. But the resolution in the preferred direction is better than the looking around resolution. But you want them to be synchronized. So what they have here is you effectively send a picture that looks like this down the stream or in the file. But you can pick out either the preferred one or the 360 one, depending on what it is that you're actually doing. So both are encoded, but the codec allows you to take sub-pictures out of that encoded picture. Phew. I think we're done.